All right, let's dive into 1.7. What we're going to be doing here, just to give you sort of a rough overview of the section, is we're going to go a bit deeper into coordinates and bases, but to really define this term dimension of a subspace. The dimension of a subspace is the number of vectors in a basis of that subspace. And this is kind of going to generalize some ideas we've already shown to be true about like RC previously, but applying those ideas to subspaces of RC in general. And we're also going to show this important theorem, which we'll get to it in a bit. There's a couple important theorems here that we're going to wrap up chapter 1 with. These are things we'll be using pretty regularly later on. Okay, so let's look at theorem 1.18 first. Properties of coordinates. So this says we have a basis with n vectors in it of a subspace U of RC. Then for any vectors y and z in that subspace and any real number k, we have the following things. If you multiply a vector y by k and then get the coordinates of that relative to b, you get the same thing as k times the b coordinates of y. So you can factor out the k from the coordinate function. And keep in mind that this isn't true for any old function. For example, sine of kx is not equal to k times sine of x. So this is something special about the coordinate function that we're talking about here. Likewise, if you get the b coordinates of the sum, y plus z, it's the same thing as the b coordinates of y plus the b coordinates of z, like so. And we also say that this coordinate function that takes a vector y in the subspace and gives you the b coordinates of that is an injective function or a one-to-one function. And what that means is that if two vectors y and z have the same b coordinates, then it implies they're really the same vector. There's only one vector that will get you these b coordinates. And part 4 says if you have any vector in Rn, then there is a y. Also notice that Rn is the number of basis vectors that we're talking about here. So saying that x is in Rn here means that the number of entries in x equals the number of basis vectors. So it kind of makes sense that x could be a basis vector of something. So at least the number of entries is right. But what this says is there is a y in U, so that the b coordinates of y is the vector x. And that means that f of y equals the b coordinates of y is a surjective, aka onto function. So anyways, let's prove 2 and 3 here. So starting with 2, what we're going to do is suppose that y and z are any vectors in the subspace U and think about what their coordinates would be. And because they're in U, we know that they can be written as a linear combination of the basis vectors. So we can assume that y can be written as like x1, b1, plus yada 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 up through xn, bn for some x, which is another way of saying we're assuming that the b coordinates of y is the vector x1 through xn. And likewise, same thing with z. So we can assume that because z is in the subspace and the b vectors make a basis for the subspace, there's some way to write z as a linear combination of those vectors. So z must have some b coordinates, and let's call those coordinates w, the w vector. Okay, so what we want to show is that we get the same thing whether we add y and z inside the coordinate vector function, or if we get the b coordinate vector first and then add them up. Well, let's see what happens if we add up y plus z. You could write it like that, but then we could also rearrange the terms, use a distributive rule, and write this as x1 plus w1 times b1, bringing those together and factoring out the b1, and do the same thing with every one of the other n basis vectors. And what this means is that the b coordinates of the vector y plus z are the vector whose first coordinate is x1 plus w1, and so on. So all the coordinates are the corresponding x plus w coordinate, because that is how you get the vector y plus z using the basis vectors as a linear combination. We could just, of course, write this as the x vector plus the w vector, or in other words, the b coordinates of y plus the b coordinates of z. And that is what we wanted to prove. All right, let's look at 3. Part 3 says if the b coordinates of y equals the b coordinates of z, then y and z must really be the same vector. So let's just suppose the if part. And we want to show that the then part, the conclusion, is true. Y equals z. So whatever these coordinates are, let's give a name for them. Let's denote the coordinates of y and b relative to this basis as x1 through xn. And I can use the same variables x for this for both of these because they're equal, right? It's the same thing. And the definition of coordinates is that these coordinates are how you write both y and z as a linear combination of the basis vectors. These are the weights you use. And of course, if you can write y and z the same way, that means y equals z, which is what we wanted to show. Okay, so this is a really simple proof that uses weird notation that you're maybe not that used to. So the coordinate vector notation is naturally confusing for a lot of people. So it is important, if you get confused by these proofs or you have trouble understanding what these things are saying, to just go back to when coordinates were introduced in 1.6. So yeah, here's the definition of coordinates in the book right here. Go back, read that, write down what it means in the context of whatever problem you're doing, maybe review a couple of other things. And once you get a little bit of practice reviewing coordinates, then these kinds of problems should be a little easier. Hopefully the warm-ups helped you get ready for that too, with the exercise 3 warm-ups. Anyways, let's look at theorem 1.19. More vectors than a basis are dependent. So if you have a subspace U that has a basis with n vectors in it, then any list with more than n vectors in U is linearly dependent. Now, we're going to prove why the answer to the warm-up number 3, part C, is really no using this. So I'll just give the gist of this out loud and then write it out in a more formal way. The gist of it is that this corresponds very closely with theorem 1.10, the thing here that says if a list of vectors has more vectors than there are entries in the vectors, then it's linearly dependent. So we're actually going to use theorem 1.10 here. So let's write it out. So we're just writing that we're assuming the if part, that we have a subspace U of RC with a basis of n vectors in it. So here's our n vectors. And we're also saying we have a list with more than n vectors. So z1 through zj is a list of j vectors. And the number of them, j, is more than the number of basis vectors. Okay, we want to show that this list z1 through zj must be linearly dependent. So the trick is to think about the coordinates, the b coordinates of the z vectors. If we get the coordinates relative to this basis b, well, it's still a list of j vectors, but how many entries are in each of these vectors? Well, just like before, where we say like if the b coordinates of y are x1 through xn, there's n of them because you need n of them to match with the n basis vectors. So these are all vectors in Rn. They have n entries in each. And because j is greater than n, now we can use that theorem to say that this is a linearly dependent list of vectors. So to show that this list is linearly dependent, we want to show there's a non-trivial solution to this corresponding homogeneous equation, right? And to do that, we're going to use the dependence of the coordinates and theorem 1.18 here. So the dependence here means that there's a non-trivial solution to this homogeneous equation. And what we can do now is say, well, we're trying to show that the corresponding z vectors are dependent. So we're going to use this theorem bit by bit. First part 1, to combine these, we can say that x1, z1 plus yada 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 up through xj, zj, taking those scalar coefficients inside the coordinates. That's going to be the same thing. And then we have a sum of them, so we can apply this theorem repeated n times to combine them into one. We have something like sum of coordinates. We can turn that into the coordinates of a sum. Also, we can say that the coordinates of the zero vector are the zero vector. Like, why can I do that? Well, because how do you get the zero vector as a linear combination of the basis vectors? Well, 0 times b1 plus yada 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 up to 0 bn is equal to the zero vector, right? Put this on the side over here somewhere, I don't know. The coordinates are this, and the result is 0. So yeah, that's why that works. And Also, I forgot to write that we're using the sum theorem to combine this part. At this point, we have two b coordinate vectors that are equal, and we can conclude that the two input vectors must be equal. That we can just delete the brackets. And that is by using theorem 1.18 part 3, the part we just showed, that if the coordinates are equal, the two input vectors must be equal. And that's what we wanted to show, that we have a non-trivial solution of this homogeneous equation, right? That means that this list of vectors z1 through zj with more vectors than a basis must be linearly dependent. So yeah, that's a cool theorem, I think. We're mostly just going to use that theorem to prove theorem 1.20. That if you have a subspace of RC, then every basis of that subspace has the same number of vectors. Let's prove it. And we're going to prove this by contradiction. What a proof by contradiction means is we're going to show it's impossible for the theorem to be false. So let's say you have two different bases of u with different numbers of vectors, like if the theorem is false. So if you have two bases of the same subspace with different numbers of vectors, then one of them, whichever one is bigger, has more vectors in it than a basis, the smaller one. And theorem 1.19 says that that bigger one must be linearly dependent, and it can't be a basis. So you cannot have two bases with two different sizes. All right. So that means this definition makes sense. That's a really ugly happy face. Try that again. We can say the dimension of a subspace is the number of vectors in a basis of U. And we know that even if you have different bases of U, all of them must have the same number of vectors according to theorem 1.20. So this is well defined. So we say the dim U equals n. And if that's true, we say U is n dimensional. So as an example, this vector space here, the span of B is two-dimensional, which is maybe intuitive because it's a plane. And planes seem like they're two-dimensional, like a piece of paper kind of thing. We'll look at a couple examples here. So let's find the dimension of R3. Intuitively, you want to say it's three-dimensional, right? But why does that agree with the definition? Well, can we find the number of vectors in a basis of R3? Sure. The standard basis of R3, write it usually as E1, E2, E3. Maybe you call it like I hat, J hat, K hat in physics. Whatever you call it. This is a basis of R3, and it has three vectors in it, so the dimension of R3 is thus 3. Cool. Let's talk about the dimension of the solution set of this equation here in R3. You might recognize this from like calculus 3 if you've taken that as the equation of a plane in R3. So maybe intuitively know the answer should be 2, but let's see how to see why that is in a linear algebra sense. And to do that, we're going to use the standard method for writing the solution set of a homogeneous equation as the span of some vectors from section 1.4, which is to write the augmented matrix for this and get it into reduced echelon form. There's the augmented matrix. And let's see, I'm going to get out my calculator, do a bunch of calculations to get this into reduced echelon form. And, oh, it's already done. Okay, because there's the leftmost non-zero entry all the way on the left. That's the pivot position. It's the only non-zero entry in its column. So yeah, this is already in reduced echelon form. And we can write the basic variables and all the variables in terms of the free variables, which are x2 and x3. So just moving the negative 8x2 plus x3 to the other side, you get that x1 is negative 8x2 plus x3. x2 and x3 are just x2 and x3. That means you can write any solution, x1, x2, x3, in that form. Or you could say x2 is a scalar that you multiply by negative 810, plus x3 could be any scalar that you multiply by the vector 1, 0, 1. And thus, the solution set is the span of those two vectors, which has dimension 2. Because here is a basis of it with two vectors. Of course, they're linearly independent because of the way that each of the free variables has its own row here, where the other vectors have a 0 in those corresponding positions. So that works. Let's look at example 3. So you'd look at this complicated set. It's a subset of R4. And, well, you could factor out all the P's and Q's and T's and R's, like so. So we could write it like this. So U, in other words, is the span of these four vectors. Oh, that was a mistake. That should have been a 4, 6. 4Q and 6Q there. Okay. So you could say, oh, U is the span of these four vectors, therefore it's four-dimensional, but the problem is that it's not linearly independent. It is linearly dependent. And you could go through the method of using that theorem to like row reduce matrix and see where the non-pivot columns are and remove the non-pivot columns, just use the pivot columns. Or just by looking at it, you might just notice that the third one is equal to negative 1/2 the second one. So that one can be removed without changing the span, and the actual basis is just the other three. So the dimension of U is 3. Cool beans. We'll look at a few important theorems in the next video. The buy two, get one free theorem we're going to use a lot. And the rank nullity theorem is also pretty fundamental in linear algebra. So that will close out chapter 1. I'll see you in the next video.